Hello friends, I Suraj. Welcome to my channel Mathematical Wizard. This is my second video and I am going to teach about inverse function theorem today. So let's begin. First we write the theorem. Theorem says that it is given here that f e to Rn is a C1 mapping where E is a subset of Rn. And it is given that f dash a is invertible. A belongs to E. We have to show that there exist open sets U and V जो belongs to Rn such that A belongs to U and Fa belongs to Ve, and Fu equal to V is 1 on 2. And also to show that G, which is the inverse function of f from V to U, is also a C1 mapping. C1 mapping means that any function is continuously differentiable. That means if f is C1 mapping, then f dash is continuous. So we have proved. So first in this video we only proved the first one. For this, let f dash a is equal to a, capital A, and we take lambda such that this one, if multiplied by 2 pi, then is equal to 1. We give this equation number 1. Chunki f dash is continuous from here, f dash is continuous, then there exists an open ball U from E having center A and radius lambda, then for any point x from U we have f dash x minus a mod of this one is less than lambda, and we give this equation number 2. Now we define phi a function as phi x is equal to x plus a inverse into y minus fx, such that x belongs to E and y belongs to Rn. Then and we give this equation number 3. Then from 3 y we can see clearly that y equal to fx if and only if phi x is equal to x. And now we differentiate the equation number 3, that is phi dash x is equal to 1 plus a inverse 0 minus m dash x, which is equal to 1 plus a inverse minus of m dash x. We can write it as and also here it will be. Then using the above result we can write it as this. We give this equation number 4. We can see from here that if x1 and x2 belongs to U, then phi x1 minus phi x2 is less than equal to phi dash x into mod x minus x2. It comes from mean value theorem. We can write it as from here is doing 4. We give it as number 5. Now we have to show here the contraction theorem. Contraction theorem. If any set x exists and a mapping phi from x to x such that for 2 points x and y belongs to x, and here 2 points which is image of x and y, phi x phi y. If phi x minus phi y mod is less than c into x minus y, c is less than y, then we call phi as a function which is a contraction function from x to x, is a contraction function from x to x. So phi is a contraction from x to x. So we can see here that this phi is also a contraction mapping from u to u. As half, we can take half as c, which is less than equal to 1. That is phi is a contraction mapping from u to u, and from contraction mapping we know that the function phi, which is a contraction mapping, has at most a fixed at most one or a single fixed point in u, say x, that is phi x is equal to x. It means that phi is fixed at the point x belongs to u. This implies fx is equal to y. It comes from this one equation. Now it means that f u to v is 1 onto mapping where v is equal to f of u. This is concluded by the theorem that here for any y belongs to v, there exists one and only one point x from u such that f of x is equal to y. So we can conclude here that f u to v is 1 1 to mapping, and this result came from contraction theorem. Now we have to show that v is an open set. For this, let y belongs to v. This implies there exists x naught from u such that f of x naught is equal to y, as f is 1 1 to mapping. Let B is an open ball centered at x naught and having radius r, which is so small such that closure of B belongs to or contained in U. Now, to show that B is open, we will show that B contains an open ball centered at y naught and having radius pi r. That is, if y be any point such that mod of y minus y naught is less than pi r, then y must belongs to B. If we proved from this one to this one, then B becomes an open set. Now we have from equation 3 we show here this one. From this one equation we use this, that is phi of x naught minus x naught, taking mod of it, will be less than A inverse y minus this one mod. This is nothing but equation 3, where we only replace x by x naught. So we can write from here y minus fx naught and is less than equal to one by 2 pi and pi r. This comes from here, where fx naught is equal to y naught, which is less than equal to r by 2. Now for x belongs to closure of B, we have phi of x minus x naught is equal to phi x minus phi x naught plus phi x naught minus x naught, which is less than equal to phi x minus phi x naught plus phi x naught minus x naught, which is equal to half. This comes from equation number 3. No, it comes from equation 5, and this comes from here, less than equal to r by 2. As this x and x naught both points belong to B, so the radius of B is r, so it will be less than r, and which is equal to or less than r. Now we conclude that phi is a contraction mapping from B closer to B closer, and this result comes from this equation. Also, B closer is closed in Rn. We know that closure of any set is a closed set. This implies B closure is complete, and also phi is a contraction mapping from B bar to B closure. So by contraction theorem, phi has at most one fixed point. Say it is x, then phi x will be equal to x. This implies phi x is equal to y. This implies y is equal to fx, which is belongs to or subset of f B closure as x belongs to B closure, and which is subset of f u as B closure is a subset of u, and which is equal to b. So this implies y belongs to b. This implies b is an open set. We have to show that y belongs to b because we want to show b is a open set. Thus we have proved the first part of our proof theorem, and that's it for this video, and the second part I am going to prove in the next video. So if you like this video, so please subscribe my channel and also share this video to your friend who is interested in mathematics, and please like my video. So that's it. Thank you.